Welcome to today's webinar. My name is Marco Perez. I'm a product manager at the Modal Shop. We'll be talking about modal testing today. I'm going to review some of the practical aspects of modal testing and shakers and stingers and things you gotta look at when you're setting up your experimental modal setup. And many of you may be already familiar with modal testing or maybe starting in this area, but experimental modal analysis is something that's been quite a popular technique in many areas, from aerospace, automotive, all sorts of R&D, and even some medical applications. So we've seen that in many different products and applications and structures. And for those of you that are not very familiar with modal testing, here's a picture of a couple of mold shapes on a very simple structure. We are talking about it's a T-shaped plate, and that's being excited by a modal shaker. So this is basically some of the results you're getting out of this testing. You're looking at the different natural frequencies of this plate, the different mold shapes, and as you do the testing, you obtaining what we call the frequency response functions, and the different peaks, the different resonances, and also the amount of damping associated with each one of those modes of vibration. So when you look at a complete modal shaker setup, there are several different components that are involved on the testing. And the two primary things we want to look at, you have the shakers, the transducers, the accelerometers, the shaker amplifier, all the different hardware pieces. You also have all the electronics associated with the data acquisition system. So you have your exciting the structure, you have an accelerometers mounted over the structure going into a data acquisition system through a signal conditioning. A lot of times the signal conditioning, it's already built into the data acquisition. And today's, there's been a lot of improvement on the robustness of software and data acquisition, 24-bit systems, but despite you may be using the best software, best data acquisition system out there, the old adage goes, if you have, bad data, it's garbage in and garbage out, regardless of how good is your system. So we're going to take a closer look at the different components of the modal shaker setup, starting with the transducers and kind of highlighting the important aspects of each one of those components. So one of the first things we want to look at is with respect to sensor selection. So you have a shaker exciting a structure, the amount of force input you're putting to the structure needs to be measured, and that's typically done using a traditional piezoelectric quartz force transducer. That's what you see here at the very bottom of the screen. And maybe about 15, 20 years ago, impedance heads were designed and came up and became popular. With the impedance head, it's a sensor that was specifically designed for modal testing applications, and that sensor can measure both force and acceleration at the same point, at the same driving point that you are inputting the force into the structure. So those impedance heads are very popular. They typically measure up to 50 pounds force, or about 200 newtons. And a lot of those sensors are also available with TADs, and so they are plug and play when you connect that to a data acquisition that supports the TAD's capability. And one important thing about those sensors when it comes to mounting is the orientation. So those sensors have a polarity associated with them. So they have a right way to mount it to the structure. That has to do with the calibration of the sensor. So you see on the force sensors, you're going to see a top label, and when you're looking at an impedance head, you're going to see a message saying mount this end of the sensor to the test structure. And the way you're going to mount that to the structure, typically, a stud mount, it's a very common way to do the mounting. There are different types of adhesives that you can use. Some people like to use epoxy, super glue, or even dental cement. And there's even some strain gauge adhesives that people like to use. Depending, where you're mounting the sensor to, you got to make sure if you need to clean up the glue afterwards or not. You've got to take that in consideration. And one common mistake we see a lot of times when it comes to shakers and stingers and connecting that to the structure is, where to mount the sensor. You don't want to mount the sensor on the shaker. You want to mount the sensor directly on the structure. If you put it on the shaker side, the whole idea of the sensor, you want to decouple the structure from the shaker. So you want to measure the vibration going into the structure. You don't want to measure the vibration from the shaker. So if you have the sensor mounted on the shaker, basically the stinger and its stiffness and mass becomes part of the structure, and that will interfere on your measurement. And we did a test. We look into that just to make sure we're not just saying that. So we did that same testing, putting the sensor on the right and the wrong position. And as you can see on the next, on the measurement results, it's very clear. On the left side, you can see a very clear driving point, frequency response function with the peaks and the resonances. And on the right side, you can see the degradation of that same measurement just because, you start to, the stinger starts to act as a mechanical filter between the shaker and the structure. So once again, never mount the transducer on the shaker side, always on the structure side. So the next point I want to jump into are the shakers. And typically, we use electrodynamic shakers. And the nice thing about electrodynamic shakers, they're very easy to drive and control. And here's the equation, the principle behind an electrodynamic shaker is an electromagnetic force where you have a current wire in a magnetic field. So when you drive an alternate current through that wire, you create an alternate force that basically that vibration that causes the vibration or the excitation into my structure. And typically the small size shakers, they would use permanent magnets. As you go into a little larger shakers, we typically replace the permanent magnet with an electromagnet and an electromagnetic field. And if you look around, you'll see that electrodynamic shakers, they come into all sorts of colors and shapes. And what we want to focus today are the modal shakers. And the one thing about modal shakers, the way we define modal shakers, we define that based on the application specifically. Those are shakers that have been optimized for modal analysis. And there are essentially two things. There are two key aspects to the modal shaker design. One aspect is the through-hole armature, which is a key benefit of a modal shaker, and that will allow you an easy connection of the stinger through a chuck and collet system. We'll detail that in a moment. The other thing to highlight about modal shakers is the fact that those shakers are not designed to support the structure directly. The structure will be supported through bungee cords or through a vibration isolator, an air ride, or a foam. So the shaker is only providing the dynamic excitation into the structure. It's not really withholding the static weight of the structure. So those two aspects are key when it comes to a modal shaker design. And the first thing that I wanted to highlight is the through-hole armature design. So if you look at the inside of the shaker, you're going to see the typical modal shaker will have a hole that goes all through this red line where the stinger can slide through it. So when you're finally you set it up in front of the structure, you can get the stinger with the perfect length, the perfect distance between the shaker and the structure you're testing. So other parts of the shaker you can see here on the picture. Of course, you can see the magnet inside, and you can see a two-layer suspension system that what holds the armature together and align the armature so the shaker can move up and down. But still, when you look at the through-hole armature design, here are the key elements on your setup, in your shaker installation. So you have your test structure that you're trying to vibrate, and of course, you got a force sensor or an impedance head. You're going to attach the stinger to it using a threaded tip stinger. And what the stinger does, the stinger can slide through the body of the shaker, and you have a collet here, and that collet, basically works like a drill bit. You're going to have the chuck piece that will tie up the collet so it grabs and compresses the stinger and holds it into its place. And one other aspect when you're compressing that collet, you always want to make sure you're using a counter wrench. So you have one wrench that's holding, you're not applying any torque into the flexures and the armature that I mentioned before. You're just compressing the collet to hold the stinger in its place. So we want to show you a quick video here that we had this video on our website for many years, and the video gives you a very easy explanation what I just said. You have the shaker, you have the structure. I'm gonna play that again. So essentially you got the stinger, it's slided in and out of the shaker. You first connect that stinger to the sensor. In the picture here on the video, we have just everything is being hand tied, but of course, you can use the wrench and the counter wrench on the chuck end to do a final adjustment there. So we don't have time today, but I want to encourage you guys, if you have some time, we have a YouTube channel. You can go to YouTube and /ModalShop. You can look at, there's a very nice video there. It's about 5 minutes long where we go step by step on a tutorial on everything I just mentioned, from the sensor mounting to the shaker connection alignment. So it's a very interesting video to watch. So just take a look at after this webinar. One more thing, a frequent question we get at the Modal Shop is, how many shakers do I need for my test? And the answer to that question really depends on what we call the observability assumption. So you basically you want to have enough shakers to properly drive or excite the modes of interest, so you can observe them. And the way of doing that, is typically, if you can, using 2 or more shakers, what we call a MIMO arrangement. It's a multiple input, multiple output configuration. So by having more shakers, you can better distribute the energy throughout the structure, and you can more effectively drive the various modes of interest. The MIMO technique also helps when you have repeated routes or closed space modes. So it helps you identify those modes better. And of course, you know, the number of shakers you can use is also limited by, you know, how many shakers you have available and how many uncorrelated sources you have to drive those shakers. But just as an illustration there, you know, we see a lot of automotive modal testing being done from, you know, using 2 to 4 shakers at the same time. On airplanes, you know, I've seen people using anywhere from 3 to 8 shakers. It's just a rule of thumb, you know. We've seen people, I mean, there are exceptions. We've seen people even using more than 8 shakers on large airplanes. Of course, if you have a small size structure, you know, a lot of times, you know, 1 shaker is enough to drive that structure. Some people ask, okay, if I put it on an orthogonal orientation, I'm going to get some of the orthogonal modes. You know, one way, you know, a lot of people like to do is to install the shaker on a skewed orientation where you can better excite different modes on the orthogonal direction, on the side-by-side or vertical. So you can get most of the modes in one shot using a single shaker. Another question about force levels. So when it comes to experimental modal analysis, no, more force is not better. Okay? And basically with the modal analysis, the assumption we make, you know, we're talking about linear structures and, you know, linear test levels. So if you're putting too much force into a structure, you know, you always have the risk of overdriving it and starting to drive some nonlinear characteristics of the structure. And again, if you can use multiple shakers, you know, definitely you can better distribute that energy, and the force levels that are required are definitely lower. So the rule of thumb here is just enough is better. And of course, because you're working with lower forces, you want to make sure you can measure the vibration response of the structure. So to help on that, it's very important to select the right sensitivity accelerometers. So we typically work with 100 millivolts per G or 1 volt per G accelerometers. And of course, you know, make sure you have a high quality, high dynamic range data acquisition FFT analyzer. And most 24-bit analyzers these days have a very, very nice dynamic range. And one thing that related to shakers is the size. And a lot of the new designs of modal shakers are very compact and lightweight, and that has been possible through the evolution of materials and technology, especially with the magnets. You know, we are able to design shakers that have the same force ratings as shakers from 30, 40 years ago, but a much smaller size. So those are very efficient shakers when it comes to force output over weight of the shaker. And the nice thing about having a lightweight shaker, those are easier to handle. The portability is a key thing, especially if you're dealing with multiple shakers and multiple excitation points. And it's also easier to fixture. We'll talk about that in a second, when it comes to shaker mounting. Yeah. So in shaker mounting and alignment, that's really can be a challenge when it comes to a shaker setup. You want to make sure your shaker is properly mounted and properly aligned in relation to the structure. And the through-hole armature helps tremendously with that because it facilitates the stinger attachment and the alignment. And there are two basic types of mounting we're going to look at: floor mounting and suspended mounting. If we look at the first example on the screen, we're looking at the shaker sitting on the floor, and to illustrate the alignment, I have added 2 stingers, one on the sensor, one on the shaker, so you can easily see the angle. So what I'm doing, I'm rotating the angle on the shaker to get to the right alignment. And once I have the right angle, actually, what I'm doing, I'm moving the shaker forward a little bit. Of course, removing one of the stingers, since I don't need 2 stingers, just need one, and then finalizing my setup. So yeah, the next picture is the final setup with the shakers sitting on the floor. My sensor was pre-installed on the structure using some dental cement. And one final touch here, some people like to apply a bit of hot glue here where the shaker is sitting on the floor, so you can add some glue there so that thing doesn't move. And one other nice thing about the chuck and collet system is, if you have to take a break for lunch, or if you stop in the test and coming back next day to finish up, you can easily disconnect the shaker from the structure, just untie the collet, and that's very important. If something happens, somebody hits the structure, or even like during the night, if the structure sags, and so you would, by disconnecting the shaker to the structure, it's a good practice to avoid any type of damage to the structure itself, or even to the shaker if things move accidentally, or just move because they moved overnight. In the next slide, we are seeing an example of a suspended mounted shaker, which, this kind of configuration allows us to easily apply some lateral input into a structure. And at this particular example, I'm pushing against the structure, so everything is in a free condition. And a lot of times we like to add a little bit of weight to the shaker. We can apply some inertial blocks to the bottom of the trunnion base on the shaker, so you get a little bit more oomph when you are pushing against the structure, especially if you're doing some very low frequency excitation, where typically you get a little bit more of displacement on the settings. And we have a variety of stingers. We mentioned the stingers. That's the little rod, or sometimes called a quill, that connects the shaker to the structure. And the one thing to highlight about stingers, basically they are the mechanical connection between the shaker and the test article. So they gotta be stiff on the direction of the excitation. And you also want the stinger to be relatively weak on the transverse direction. So that way it will help you with any type of potential side loading that can be applied to the structure due to a little bit of misalignment, or due to the vibration or rotation of the structure as you run the testing. So minimizing that transverse loading, it's important, because again, the excitation you're putting on is in the axial direction, and also the sensor we are using here, it's a single axis sensor. We only measure excitation in one direction. The other thing about the stinger is it also functions as a mechanical fuse. So, the stinger is just a little piece of metal that doesn't cost a lot. So if something happens and again, something catastrophic, or something falls, or you may end up bending the stinger, which is easily replaceable, but you are alleviating any potential mechanical damage that can happen to the shaker or to the structure. So typically you're going to damage the stinger, you replace it. It's a replaceable item that it's a very low cost. You can put a new one and continue your testing. So as we finalize the review of the settings here, we're going to talk just a few words about the shaker amplifier. So you got to have some power. You got to be able to take that signal from your analyzer and amplify that to the shaker, so you have enough energy to drive the structure. And again, just like shakers come in different sizes and shape, same thing about amplifiers. You have, typically large size amplifiers. They're typically 19 inches wide, so you can put that on a rack. But you can also have some very small amplifiers that can be integrated with your shaker, as we see on the right. But the key things about a shaker amplifier, key things to consider are, I think the most important one is the compatibility. So you want to make sure the amplifier is compatible with the shaker. You want to make sure it matches the shaker impedance. This is very important because a lot of the amplifiers out there, especially the ones that use audio technologies, they are designed to drive speakers. And speakers are typically an 8-ohm electrical load. And when it comes to shakers, electrodynamic shakers are typically very low impedance. So you want to avoid that kind of mismatching. So the other thing that's important when it comes to amplifiers, make sure it covers the whole frequency range of the shaker. And again, this is very important because not every amplifier will operate below 20 hertz, and there's a lot of vibration testing that happens below 20 hertz. So the electrodynamic shaker can go all the way down to 1 hertz or a fraction of hertz. So you want to make sure the amplifier can respond at those lower frequencies. And of course, things like power rating. You want to have enough energy to drive the shaker to its full specifications. There are safety features associated with the amplifier. So the amplifier doesn't start in a high gain. You want to have features where you can control the amplitude on the amplifier, start slowly, fuses, and of course input power requirements. Depending of the amplifier, you're going to need 110 volts or 230 volts. Some amplifiers are single phase, typically for the small shakers. When it comes to larger shakers, you're going to see 3-phase requirements and other types of requirements. But again, most important thing is compatibility. And a lot of times, when you get the shaker and the amplifier from the same supplier, we want to make sure we test that as a system to make sure we can deliver the specifications that we promised to you. So that's it's a very quick overview of some of the aspects when you're doing the equipment settings on a modal testing, and some of the guidelines, general guidelines, and that we would like to share with you, and highlight all the details, the importance of those to make sure you can acquire high quality data, high quality frequency response measurements. So when you input all those measurements into your modal software, you can extract the modes, you can do your correlation work, you can get the results, consistent results from whatever you're trying to test. And by no means I want to cover everything here. I mean, this is just a very introductory to modal testing, but there are lots of good references online or even on our website. So a lot of the things we cover today here are highlighted on this technical article from the Sound and Vibration magazine. Again, I mentioned before the YouTube channel has a lot of good videos there. And there's also an interesting frequently asked questions FAQ document. It's available on our website. So here are the links. And I'd like to thank everyone today for attending the webinar. And please stay tuned for the next webinar from the Modal Shop. Thank you.